Then I'll share the screen. Let's start from the top, from the start. So data structure is a way to store the data uh, and organize the data so it can be used effectively. Store and organize data. Okay. Uh, there's linear data structure and non-linear data structure. Linear data structure has static and dynamic data structures, and non-linear data structure has got tree and graphs. Static, we have array. Dynamic, we have queue, stack, and linked list. Linear data structure are those data structure in which the data is in form of sequence, and non-linear, the data is not in the sequence, like tree and graph. Static means that I think the size of the data is fixed, and in dynamic, the size can vary. So data elements are arranged sequentially or linearly, where each element is attached to its previous and next adjacent elements. Example of linear data structure: array, stack, queue, and linked list. Static data structure has a fixed memory size. It is easier to access the elements in a static data structure. Example of this is an array. Dynamic data structure size is not fixed. It can be randomly updated during runtime, which may be considered efficient concerning the memory complexity of the code. Example of this structure is stack, queue, linked lists. Non-linear data structure are not placed sequentially or linearly. We can traverse through all the elements in a single run only. Example, trees and graph. We can't traverse, not can, but we can't. In a single run, we can't traverse. Then we have arrays. Array is a collection of data items, similar data type, stored in a contiguous memory locations. This is an example. We can access the values with the help of an index. And this is a Java example where the square bracket is next to the data type, and in C programming, the square bracket is the next to the variable name. Multi-dimensional array is array of arrays that uses more than one index to access the array elements. By the way, I'm not using my mic because, of course, I'm not carrying my mic, so it's just Mac speaker. Sorry, mic. Okay, so this is the dimensions, and I think we learned that the first one here is number of blocks, and this is rows, and this is column in three-dimensional array. This is how it's written in C, and this is how it's written in Java. Structures. So I think structure is a collection of data of different data types. Yeah, of one or more data types. Value of each element of the structure referred to its corresponding identifier coupled with the variable name of the structure. List. So list, I think, is a sequence of data. Is a linear data structure that consists of nodes containing the data and the pointer to the next node in the list. So there are singly linked lists, there are doubly linked lists. The difference between singly and doubly is that the singly has um, the pointer pointing to the next node, and also has the previous pointer pointing to the previous node. So we can traverse in both directions. A linked list is used to maintain dynamic series of data. Think of a linked list like a line of bogies of a train where each bogie is connected on to the next bogie. If you know where the first bogie is, you can follow its link to the next one. By following the link, you can find any bogie of the train. When you get to a bogie that isn't holding a link uh, into another bogie, you know you are at the end. Types of linked list: singly linked list and doubly. Singly is the simplest type of linked list in which every node contains some data and a pointer to the next node of the same data type. A single linked list allows traversal of the data only in one way. A doubly linked list or a two-way linked list is more complex type of linked list which contains a pointer to the next as well as previous node in sequence. Therefore, it contains three parts: data, pointer to the next node, and a pointer to the previous node. Okay. Now circular linked list. It's a variation of the linked list in which the first element points to the last element and the last element points to the first element. There are two types of circular linked list, singly and doubly. Circular linked list. In singly, the next pointer of the last node points to the first node, and in doubly, next pointer of the last node points to the previous. One second. Next pointer of the last node points to the first node, and the first node points to the last node. Next pointer of the last node points to the first node. Previous pointer. Okay. Previous pointer of the first node points to the last node. Okay. Asymptotic notation. Asymptotic notations. First, we talk about complexity, the rate at which required storage or time grows as a function of problem size. The rate at which required storage or time grows as a function. Asymptotic notation are mathematical notation used to describe the running of an algorithm when input tends towards a particular value or limiting value. So let's see. Mathematical notation used to describe running time of an algorithm when the input tends towards the particular value or a limiting value. Okay, for example, in bubble sort, when the input array is already sorted, the time taken by the algorithm is linear. That is the best case. There are okay, so an input array is already sorted, the time taken by the algorithm is linear. Okay. There are three main types of asymptotic notations. First is big O notation. Second is omega notation, and third is theta notation. And big O notation is a formal way to express the upper bound of the algorithm's running time. It measures the worst case time complexity or the longest amount of time an algorithm can possibly take to complete. We typically consult the big O because we must always plan for the worst case. For example, O log n describes the big O of a binary search algorithm. Omega notation. The notation is a formal way to express the lower bound of an algorithm's running time. It measures the best case complexity of the best amount of time an algorithm can possibly take to complete. For example, bubble sort algorithm has a running time of uh, omega n because it is the best scenario. The list is already sorted, and the bubble sort will terminate after the first iteration. Theta notation. The notation is formal way to express both lower bound and upper bound of the algorithm's running time. Okay. It is used to analyze the average case complexity of an algorithm. Time complexity. Generally, there's always more than one way to solve a problem in computer science with different algorithms. Therefore, it is highly required to use the method to compare the solutions in order to judge which one is more optimal. There are two methods. One is time complexity and space complexity. Time complexity of an algorithm is represented by the amount of time required by the algorithm to execute to its completion. And space complexity is the amount of space required by an algorithm to its completion. It can be denoted by a numerical function Tn, where Tn can be measured at the number of steps, provided each steps can take constant time. For example, in case of addition of two n-bit integers, n steps are taken. Consequently, total computation time is Tn c into n, where c is the time consumed for the additional two bits. Space complexity of an algorithm represents the amount of memory space needed by the algorithm in its life cycle. So, Maya, can you read this?
Space complexity is the space needed by an algorithm. Space needed by an algorithm is equal to the sum of the two following components.
Okay.
A fixed part, a space required to store certain data and variables, that is, simple variables, constants, program size, etc., that are not dependent on the size of the problem. A variable part, a space required by variables whose size is totally dependent on the size of the problem. For example, recursion, stack space, dynamic memory allocation, etc.
Okay. So, dependent on two parts, fixed part and variable part. Fixed part is a space required to store certain data and variable, which does not depend on the size of the problem, and variable part is the space required by variables whose size is dependent on the size of the problem. Okay.
Space complexity SP of a P algorithm is SP equals A plus SPI, where A is treated as the fixed part and SI is treated as the variable part of the algorithm, which depends on instance characteristic I. Following is a simple example that tries to explain the concept. Sum of P and Q, step 1 start, step 2 R equals P plus Q plus 10, step 3 stop. Here we have three variables P, Q and R and one constant. Hence SP equals 1 plus 3. Now space is dependent on data types of given constant types and variables, and it will be multiplied accordingly.
Okay, so to recap, complexity is the amount of space needed by an algorithm to complete its execution, and it's dependent on two parts. First is fixed part, and second is variable part. Fixed part is the space required to store certain data and variable, which does not depend on the size of the problem. That's why it's fixed. Variable part is the space required by variables whose size depend on the size of the problem. And space complexity is SPA plus SPI. A is the fixed part, SI is the variable part. Okay, running time complexity. Time complexity is a complete theoretical concept related to algorithms, while running time is the time a code would take to run, not at all theoretical. So I think when you're talking about time complexity, you're talking about that formula like n log n. But here, when you're talking about running time, it's actually the actual time. Like for example, two different algorithms can have same time complexity of n log n, but two algorithms can have different running time. So they may be linear, like it grows linearly. One of them takes 10 seconds no matter how many times you execute. Another one takes 20 seconds no matter how many times you execute that. So of course the time complexity of both of them will be constant, but the running time will be different. So the running time is the actual time it takes to run the code, not theoretical. Two algorithms may have it's saying the same thing which I just said. Two algorithms may have the same time complexity, say O n log n, but one may take twice as much running time as the other. So yeah, I doubt they'll ask, but if they ask, we know what it is. Stack. So stack is a linear data structure which is based on the last in first out, LIFO, right? I took a moment to think, get confused between queue and stack. Okay, so it just has one pointer, top pointer pointing to the top of the stack. Elements can be inserted from the top of the stack and can be removed from the top of the stack. Let's not spend too much time on this. Let's move on. Operations can be performed. So there's is empty, is full, um, is empty checks if the stack is empty, is full checks if the stack is full or not. Then you have what else there? Count. count the number of elements in the stack. Display displays all the number of all the elements in the stack. Then we have push and pop. Push pushes the item at the top of the stack. Pop removes the item from the top of the stack. uh, Peek, peek is to get the first element from the top of the stack. And what else? Which else am I missing? Is it change? Change is also there, right? Yeah, changes the element at a given position. Cool. Queues is so queue is a linear data structure, uh, which is based on the first in first out principle. So it has two ends, unlike stack, which is one end, and both operations in stack are performed at the same end, which is the top of the stack. In queue, the elements are added from the rear and removed from the front. So an example is a queue at the box office. Okay, operations perform is. So may I remember what are the operations on this one? Is it NQ and DQ?
Yes,
Okay, so
and is
NQ is
empty
to
is full.
is empty is full. Okay, NQ is to add an item at the rear, and DQ is to remove an item from the front. Correct? Yeah. Peek is oh, we missed peek. Peek to get the element at the front of the queue without removing it. Is full checks if the queue is full. Is empty checks if it's empty. Difference between stack and queue. We already know the difference is like um, queue has two ends for operations. The oh sorry, this is queue and DQ, right? Okay. So in DQ, how it differs from NQ from a queue is that both the insertion and deletion can happen from both the ends, front and rear, unlike queue where it happens only at the start. And then queues are a specialized data structure that uses FIFO, which is first in, first out. DQ can be used to implement the functionalities of both stack, which is LIFO, and queue. Okay. Trees. So trees have hierarchical data structure. A tree is one of the data structure that represents hierarchical data. I mean, the best thing to remember is hierarchical word when we talk about tree, and then we can make our definition. So it has a root node, then you have child nodes. Uh, the child nodes which do not have the nodes which do not have children are called leaf nodes. Each of the nodes can have each of the node can have value, or it can be empty also. The value of could be of any data type. What else? A tree data structure defines a collection of objects or entries known as nodes that are linked together to represent or simulate hierarchy. Collection of objects or entities known as nodes that are linked together to represent or simulate hierarchy. A tree data structure is a non-linear data structure because it does not store sequential manner. It is a hierarchical structure as elements in the tree are arranged in multiple levels. In the tree data structure, the topmost node is known as root node. Each node contains some data. Data can be of any type. In the upper tree structure, node can contain the name of the employee, so the type of data would be a string. Each node contains some data and the link or the reference of the other nodes that can be called as children. The nodes that do not have children are called leaf nodes. Okay, general tree and binary tree. General tree um, cannot be empty, I believe. Binary tree can be empty. And general tree, we can have many child nodes, but in binary tree, we can have at least two nodes maximum. And we have a left subtree and right subtree in binary tree. In general tree, There can be either zero subtree or many subtrees. In general tree, there is no limitation on the degree of the node, while in binary tree, there's a limitation on the degree of node because nodes in binary tree can't have more than two child nodes. Okay, now BST, not the bus, but the binary search tree. So, what is a binary search tree? A binary search tree is a binary tree that is either empty or has node containing a key value, a left child, and a right child. So I think what they're saying is that a binary search tree can be empty. Reverse a binary search tree. Can you reverse the binary tree? ये question है. Okay. The question was asked in Google. Let's see the answer then. There is no as a proper answer. No, you have to solve that. Oh, okay, fine. We have a new student actually, which is not joined the class yet, but yeah, he's taken admission. Okay, has a node containing a key value left child and a right child. A non-empty binary search tree satisfies the following condition: the key in the left so there is an child package developer who is well known and his packages is used by Google itself. Okay. Now he went for the Google interview, and the Google interview rejected him because he was not able to reverse the binary tree. No. So he came back and he tweeted that you use my package. The package is created by me, but you would not hire me because I'm not able to reverse the binary tree. Okay. So तब से वो क्लीशे बन गए. Okay. Fine. The key in the left child of a node is less than the key in its parent node. The key on the right child of the node is greater than the key in its parent node. The left and the right subtrees of the root are again binary search trees. Okay, so non-empty binary search tree meets the following condition: the left child node needs to contain a lesser value than the parent node, and on the right one, it needs to contain a greater value than the parent node. And the left and the right subtrees of the root are again binary search trees. Now, Avl tree. What's the full form of Avl? Avl tree is basically self-balancing trees, uh, where the difference between the height of the left tree and the right subtree cannot be more than 1 for all the nodes. Splay trees. Splay tree is a type of binary search tree that is used to splay the operation on the tree, so the most frequently used elements can come closer to the node root. A splay tree contains the same operation as the binary search tree, that is insertion, deletion, searching, but also contains one more operation which is called splaying. So to search an element in a splay tree, first we'll perform the standard binary search tree. For example, we're looking to search an element called 7. So once we get that element, as 7 is less than 10, so we'll come to the left of the root node. After performing the search operation, we need to perform splaying. Here, splaying means that the operation that we are performing on any element should become the root node after performing some rearrangement. So the rearrangement of the tree will be done through rotation. So 7 was here, we rotated the tree and brought that to the top and made it a root node. So that's what happens in splaying. Splaying, we bring the node in question to become the root of the node by rotating the tree. Red black trees. A red black tree RBT is a type of binary search tree with one extra bit of storage, that is its color. Okay, so this color can be red or black. Properties of this tree are: each node of the tree should be either red or black. Hello, Sumaya, can you hear me? Hello.
Yeah, I can hear you.
Okay, actually, electricity was gone. Now it's come back.
Okay.
Again. I'm audible, right?
Yes.
Okay, it's coming and going, so I'm just letting you know. If it goes, I'll rejoin.
Okay.
Okay, so red black trees, so they have an additional uh, extra bit of storage, which is for color. The color could be red or black. Properties is that each node could be either red or black. If the root is always black, if if the node is red, then its children should be black. For every node, all paths from a node to its leaves contain the same number of black nodes. Node Z is inserted using same procedure as binary search tree. Z is colored red. Rotation and coloring is performed to retain red black trees properties. Four scenarios. If Z is the root color is black, Z dot uncle equals red, and recolor Z's parent, grandparent, and uncle. Z dot uncle equals black, then rotate Z's parents. Graphs. So graph is a collection of vertices and edges. A set of vertices always non-empty. Edges represent the ordered or unordered pair of vertices which is directly connected to each other. Okay. What is complete graph? A graph is said to be complete graph if for all the vertices of the graph there exists an edge between every pair of the vertices. In other words, we can say that all vertices are connected to the rest of all vertices of the graph. Okay. So what they're saying is that if there is an edge between each of these uh, nodes, then it's a complete graph. Even if one of them don't have it, like if B and D don't have a connection with an edge, then it's not a complete graph. So each of the node need to be connected by vertices. Sorry, by the edge. Node is same as the vertex. Okay, a spanning tree. A spanning tree is a subset of a unidirected graph that has all vertices connected by a minimum number of edges. A minimum spanning tree is a subset of edges of a connected weighted graph that connects all the vertices together with minimum possible edge weight. We can use Prim's algorithm, Kruskal's algorithm. Kruskal's algorithm is used to find the minimum spanning tree. And what is a spanning tree? A spanning tree is a tree that is a subset of unidirected graph that has all the vertices connected by minimum number of edges. And here in Kruskal's algorithm, you need to find the minimum spanning tree for connected weighted graph. The main target of the algorithm is to find the subset of edges using which we can traverse every index of the graph, or every vertex of the graph. So let's see, I'm not going to do here, I'll just take a look at this example. So let's say there's a graph. First, we will put the edges and their weights and then reorder them to put them in an ascending order. Then we start plotting them like so. So we add the edge AB and its weight to the minimum spanning tree. Then we add the other one. If anytime they are completing a cycle, then we reject that particular edge. Otherwise, we continue until we have finished with all of the edges. And then finally, some of these edges is actually the cost of the minimum spanning tree. Moving on. Shortest path algorithm. Shortest path algorithm calculates the shortest path from a start node to each node of a connected graph. Let's keep a target to end it by 8 o'clock. I hope that's okay.
Yeah.
Okay. Shortest path algorithm calculates the shortest path from a start node to each node of a connected graph. Example, Dijkstra's algorithm. Okay, it's the shortest path from the start node to each node. Yeah, I should highlight that. Shortest path, start node to each node. Okay, so this is Dijkstra's algorithm. I hope I'm pronouncing it right. It's a single source of shortest. It's a single source shortest path algorithm. Here, single source means that only one source is given. We find the shortest path from the source to all the nodes. Time complexity is OV2. Applications are to find the shortest path in social networking applications, telephone network, and to find the locations in the map. So you first just select any of the single source, the main source. We give it the weight, let's say 0, and then to the rest of the nodes or vertices, we just put them as infinity. Choose a node, example 0, assign 0 to it, and assign infinity path values to all other nodes. Then start from the source node, update the adjacent nodes with the minimum weight, that is the distance from source node. In this step, the adjacent nodes are 4 weights apart from the first node. So we update 4 and 4. Then traverse to the next adjacent unvisited node that has the minimum distance from the source node. So in this case, both have minimum distance, so let's go with this one. Okay. Then update the weight of all the next adjacent node values, keeping in mind that the calculation is done considering we traverse from the source node through the currently visited node. So adjacent is this one because this adjacent is already filled. So what's the weight of this? It's 4 plus 2, which is 6. Now 6 is greater than 4. That's why we're not going to update that, because we have to keep the minimum shortest path basically from the source. If the shortest distance from the source node to the adjacent node is less during that traversal, then don't update the node, like we just discussed. Repeat this process until all nodes are visited. Depth first search with an example. A standard depth first search implementation puts each vertex of the graph into one of the two categories. First is visited, second is not visited. The purpose of algorithm is to mark each vertex as visited while avoiding cycles. The DFS algorithm works as follows. Start by putting any one of the graph's vertices on top of the stack. Take the top item of the stack and add it to the visited list. Create a list of that vertex adjacent nodes and the one which aren't visited list to the top of the stack. Okay, so here it is. Let's see how the depth first search algorithm works with an example. We can use a unidirected graph with 5 vertices. We start from vertex 0.
Undirected.
Undirected? Okay, I keep doing that mistake. Thanks. Okay. And what's the meaning of undirected? Not in a particular direction?
Means the edges don't have any direction.
Okay. We start from vertex 0. The depth first search algorithm starts by putting it in visited list and putting all its adjacent vertices in a stack. And I think the reverse is true for breadth first search. We start from the vertex 0. Okay, we already done that. Next, so we put 0 and then we put the adjacent vertices, which is 1, 2, and 3, into the stack. Next, we visit the element at the top of the stack, 1, which is 1, and go to its adjacent nodes. So we visit 1 and we put that in the visited. And of course, now we have to find out what are the adjacent uh, nodes or vertices, and we need to put them in the stack. So from 1, we have 2 and we have 0. Now, 2 is already present, so we don't do anything. Now we visit the next one in the stack, which is 2. We put that in the visited, and now we need to find out which are the adjacent vertices. So adjacent vertices is just 4 because 0 is already visited and 1 is already visited. So 4 is there. So we're going to push 4 into the stack. And since stack uh, says that you can put the elements from the top, that's why it's getting inserted from the top. If this was queue, then we would have been adding elements from the rear. Okay, so now we have 4. So we visit 4, we put that in the visited, and let's see. From 4, we already have everything visited, so we don't need to worry about anything. Now we visit 3, we put that in the visited, we don't have anything, stack is empty, the job is done. So to sum it up, depth first search puts each vertex of the graph into two categories, visited and non-visited. The purpose of algorithm is to mark each vertex as visited while avoiding cycles. Start by putting any of the graph's vertices on the top of the stack. Take the top item of the stack and add it to the visited list. Create a list of that vertex adjacent node. Add the ones which are not in the visited list at the top of the stack. Keep repeating the 2 and 3 until the stack is empty. Red search, same thing. Instead of stack, we use queue. Search algorithms. Linear search. The elements are searched in a linear fashion, which means we loop through the list from top start to finish until we encounter that element. If we find that element, we return that element. Otherwise, we return the index of that element, or we return -1. Binary search with example. So binary search is searching algorithm used in sorted array by repeatedly dividing the search interval into half. Okay, so the idea of the binary search is to use the information that array is sorted and reduce the time complexity to O log n. So we use it in a sorted array to repeatedly divide the array into search intervals in half. So begin with the mid element of the whole array as the search key. If the value of the search key is equal to the item, then return the index. If the value of the item to be searched is less than the mid element, then decrease the interval to the left half. Otherwise, decrease it to the right half. Repeatedly check from the second point until the value is found and interval is empty. So basically, we divide the array into half. We go to the mid element. If we find the match, we return it. If not, we compare it. If the value that we are trying to search is less than the mid element, then we uh, basically reduce the list into left half, otherwise right half, and then we repeat the same process. Sorting algorithms: internal sort, bubble sort, quicksort, two-way merge sort, heap sort, and topological sort. Three divide and conquer techniques. So one is two-way merge sort. Then we have binary search, and then we have, is it quicksort? That's the third one.
Yes.
Okay. I'm going fast so we can cover more. I hope you're okay with the speed, yeah?
Yeah, it's fine.
Okay. Insertion sort. This is naturally occurring sorting method exemplified by a card player arranging the cards dealt to him. He picks up the card as they are dealt and inserts them into required position. This is at every step we insert an item into its proper place and an already ordered list. To find the correct position, search the list till an item just greater than the target is found. Shift all the item from this point one down the list. Insert the target in the vacated slot. Repeat this process. So basically, there are two. Yeah. So basically, what we need to do is we need to loop through that list, and we need to find an item which is just greater than the one we are trying to insert. Once we find that, from that position, we start shifting all the items towards right. So this will create an empty space, and that's the place we insert our element. Next, I'm just going to skip this. Bubble sort. In bubble sort, we repeatedly compare the adjacent elements, and if they're not in order, we sort them. Sorry, we swap them. In bubble sort, we repeatedly swap the adjacent elements if they're not in order. This algorithm is not suitable for large data sets as its average and worst case time complexity is quite high. This is an algorithm. Can you read this?
Write an algorithm to bubble sort in ascending order.
Yeah.
Step 1, begin. Step 2, read the array and length of the array, n. Loop from second element to last element for I equals 1 to n. Loop from last element to current element for j equals n minus 1 to I. Swap two adjacent elements if they are not in order. If array j minus 1 is more than array j, swap array j minus 1. End.
Okay, so we read the array and the length of the array. We loop from second element to the last element, and then that will be the outer loop. And the internal loop will be last to the current. And then we compare. If the adjacent elements are not in order, then we solve them. These are all the steps. Quicksort. I think quicksort is the one where we have the pivot, right?
Yes.
Yeah, let me try to recall. Let me see if I remember it. So what we do is we first choose a pivot, and then we move the pivot to the right, extreme right. Then the rule for the pivot is that after once we sort it, it should be in a way that uh, all the elements on the left of the pivot need to be smaller and on the right needs to be larger. So once we follow these steps and move the pivot to the extreme right, then we compare. We actually find the first element from the left that is larger than the pivot, and we find the first element from the right which is smaller than the pivot, and we swap them. We continue this process until the left is greater than the right. The left element is greater than the right. If it is, then we stop there, and then we swap the position of the pivot to bring it back to its original position. Then at this point, uh, we'll see that the elements are in basically satisfying a pivot rule, which is elements on the left of the pivot are greater, are smaller, and on the right of the pivot are greater. Then we break the pivot into two parts. We take the left part and follow the same algorithm that we just spoke about until the elements are sorted, and then we follow it on the right also, and then finally let the recursion handle it. Did I miss anything?
I think that one step is to swap the pivot with the left item from left, not to bring it back to the original position.
Okay, so it's not actually bringing back to the original position, but it's actually swapping it with the item on the left, correct?
Yeah.
Okay, cool. Thanks. Hey, wait, quick sort. Ah, that's the one. Yeah, correct. Okay, I'll move on. Heap sort. So I think in heap sort we do some heapify stuff. So let me try to recall this first. So let's say we have a list of item. We first put them in a binary, not binary, but we just put them in a tree. And once we put them in the tree, then we kind of rearrange them in a way that satisfied the binary tree, I believe, which is the element on the left need to be s- smaller than the parent, like the child needs to be smaller than the parent on the left, and on the right, the child needs to be larger than the parent, and of course the root needs to be the largest. So once we arrange them in that way, then we place them back into that list, and then uh, what we're going to do is we will consider a space in the list which will contain the sorted items. So, for example, 9, we'll put the 9 at extreme right, and then treat the rest of the elements in the array to be sorted again in a similar fashion. And then we repeat the same process. So, what am I missing here, Sumaya?
We have the heap condition,
Yeah,
which is the children should all be smaller than the root. It's not the same as the binary search tree.
children need to be smaller than the root. Okay. Is it just the root or the parent?
The parent.
What about the left and the right rule? How does that work?
That one is not there here.
It's not there. Okay. Let's see. Heap sort works by visualizing the elements of an array, a special kind of complete binary tree called a heap. Okay, so we visualize the elements as a special kind of complete binary tree called a heap. Complete binary tree is set to satisfy the heap condition if parent node value is greater than or equal to child node value. So the root will always have the largest value. Heaps are represented as arrays by first numbering the nodes starting from the root from left to right. Build a heap with the items in order presented. Modify to satisfy the heap condition. Build max heap. Swap, remove the root element and put that at the end of the array, nth position, and put the last item of the heap at the vacant position. Reduce the size of the heap by 1. Heapify. Heapify the root element again so that we can have the highest element at the root. So I think constantly we have to aim to get the highest element to the root. And another condition which you mentioned was the parent node value needs to be greater than equal to the child node value. So let's take a look. So this is our list. We put them like so. So 2 goes here, then 8 and 5 goes as children, then 3 and 9 goes as this children, and then 1 goes here. Then we sort them in a way that the parent has, the children are smaller than the parent, right? So parent needs to be higher or equal to. So we'll start from here, I think. So is parent larger? Yes. So we leave that there. Is parent larger? No. So we'll swap that. So 9 comes here. Is parent larger? No. So we'll push. I think we have to start from top or something. I think I'm doing it wrong. So start from here. Yeah, I think let's start from here. So 2, 8. We swap 8 and 2. So 2 comes here. And 2 and 9. We swap it. One second. Swap 9 comes here. Yeah, let's start from the bottom only. Swap this, 8 comes here, 9 comes here. Then swap it, 9 comes there, 2 comes here. Again, you have to swap, I guess. You have to keep swapping them until the condition is met. So finally, we'll have 9 at the top. We place all of them in the list and then move the 9 at the end, like swap the first and the last. We did that. So this comes here. Again, we place them and we just keep repeating the same process. Two-way merge sort. What do you remember from this? The merge sort.
So merge sort works by repeatedly dividing the array into halves
Yep.
uh, until it cannot be divided any further. And
Yep.
then the sub arrays are merged together uh, in a sorted fashion.
Yep. Absolutely correct. Can you read it?
Merge sort is a sorting algorithm that's based on the divide and conquer strategy. Merge sort continuously breaks down a list into multiple sublists until each list only has one item, then sorts each sublist and merges those into a sorted list.
Mm-hmm.
Algorithm check if the left index of array is less than the right index. If yes, then calculate its midpoint. Divide the array into two halves using its midpoint. Further divide these two arrays into further halves until the atomic units of the array is reached and further division is not possible. Start merging the elements again based on comparison of size of elements. Compare the element for each sublist and then combine them into another list in a sorted manner.
Okay. So merge sort is a sorting algorithm that's based on divide and conquer strategy. So there's merge sort, there's quicksort, and there's binary search. These are the three ones that are on divide and conquer strategy, right?
Yeah.
Okay. Um, we have to continuously break down the list into multiple sublists until each list only has one item, then sort each sublist and merge those into a sorted list. Check if the left index of the array is less than the right index. If yes, calculate its midpoint. Divide the array into two halves using its midpoint. Further divide these two arrays into further halves until atomic units of the array is reached, and further division is not possible. Start merging the elements again based on the comparison of the size elements. Comparison Compare the elements of each sublist and then combine them into another list in a sorted manner. Left is less than the right, mid equals left plus right divided by 2, then merge sort on A left and mid, merge sort A mid plus 1 right, merge A left, mid, and right. Topological sorting, moving on. Java. I think what we should do now is for the next 18 minutes we've got, we should do database management. We haven't done that so far. So we did Java yesterday, so we could skip that today. Yep, here it is. Relational Database Management System RDBMS is based on relational model introduced by EF Cord. An example is SQL, MS SQL Server, IBM DB2, Oracle, MySQL, Microsoft Access, or RDBMS. SQL, MS SQL Server, IBM DB2, Oracle, MySQL, and Microsoft Access. So RDBMS database uses tables to store data. Each table is called a relation, which is a collection of related data entries containing rows and columns. So it uses tables to store data, and each table is called a relation, which is a collection of related data entries containing rows and columns. Each table represents some real world object such as person, place, or about or event about which information is collected. Name some DBMS technologies. They are RDBMS and NoSQL database. In RDBMS, we have SQL, MS SQL Server, IBM DB2, Oracle, and MySQL and Microsoft Access. In NoSQL, we have MongoDB. There's one more. AWS DynamoDB. Difference between relational and object-oriented database. Apart from the, of course, the full form, data is stored as entities defined in tabular format. in RDBMS, and data is stored as objects in OODBMS. RDBMS handles simple data, OODBMS handles large and complex data. An entity refers to a collection of similar items. So I think the point 2 and point 4 are related. So data is stored as entities, and the entity meaning of entity is like collection of similar items having some definition, same definition. A class refers to a group of objects having common relationship, behaviors, and properties. So point number 4 basically talks about defining what an entity is for an RDBMS, and for OODBMS it talks about what a class is. Data handling. RDBMS handles only data. OODBMS handles both data and functions operating on that data. Uh, Objective is to keep the data independent from application program, and OODBMS to keep the data encapsulated. Okay, so keep data independent from the application program and keep data encapsulated. Okay, a primary key identifies an object in a table uniquely. Object ID is used to uniquely identify a group of objects. So here primary key is used, and there you have object ID. Okay, each row of the table is called record or tuple. Each column is called an attribute that represents the values. A domain is a set of permissible values that can be accepted by a specific attribute. Smallest unit of data in the table is called data item or cells. So these are rows are basically tuple, columns are attributes, domain is the range or the permissible values. Total number of attributes that comprise a relation is known as degree of the table. A superkey is an attribute or set of attributes used to identify the records uniquely in a relation. Employee is a superkey since employee is unique for each tuple or record. Similarly, employee ID, ename, and employee ID post are also superkeys of a relation. Employee, since their combination is also unique for each tuple or record. Candidate key is a single key or a group of multiple keys that uniquely identify rows in a table. Example, both employee ID and name can act as a candidate for table as long as they contain unique and non-null values. Candidate key should be as small as possible. Difference is that candidate key is not reducible, which means after removing one attribute, the other attribute should not unique itself. Primary key is a candidate key selected by. Was the question called what is primary key in the Viva from Mumbai?
I don't think so.
There was something about the key, right? There was. Check it later. Okay, so primary key is a candidate key selected by the database administrator to uniquely identify tuples in a table. Out of all the candidate keys that can be possible for a table, there can be only one key that will be used to retrieve unique tuples from the table. So out of all the candidate keys, there can only be one primary key. Okay. Relation is defined using two aspects. Relational schema specifies relation's name, list of attributes. Relational instance is a collection of tuples, collection of rows. Can you read this? I'm tired.
Yeah, there is primary key in the questions. Primary
I
key, an
don't
example of primary key.
remember that. Cool. Let's read it.
Relational constraints and types of constraints. On modeling the design of the relational database, we can put some restrictions like what values are allowed to be inserted, modified, deleted in the relation. These restrictions that we impose on the relational database are called relational constraints.
Mhm.
Constraints are of the following types: domain constraints, key constraints, integrity
Oops.
constraints.
Okay, so constraint basically restrictions that we put to what value we're going to allow the user to insert, modify, or delete in relation. And there are different types: domain, key, and integrity.
Domain constraints. These constraints bind the possible values of attribute in a relation to a specific set of the given data type, called the domain of the attribute. Every domain must contain atomic values which cannot be divided into subvalues. This means composite, which can be divided into subparts, and multivalued attributes are not allowed.
Okay, this constraint bind the possible values of the attribute in relation to a specific set called the domain of the attribute. Every domain must contain atomic values which cannot be divided into sub values. So then key things to remember is that cannot divide uh, value into sub value in a domain. That's domain constraint. So multi-valued attribute are not allowed. For example, the phone number there, so multi-valued, it's not allowed. Okay, so this was on domain, which is this. And now we talk about the key, related to the key. So earlier was domain, and this is key. Okay, go on.
Key constraints. This constraint states that the key attribute value in each tuple must be unique. That is, no two tuples can contain the same value for the key attribute.
Okay, so key attribute in each value must be unique, so no tuples can contain the same value for the key attribute. Like in this case, we have two records or two tuples with the same ID, which is incorrect, which is kind of violating this constraint. So no two tuples can have the same key value. That's the thing. Okay, you saying something?
Integrity. No.
Okay.
Integrity constraints are of two types: entity integrity constraint and referential integrity constraint. Entity
Okay.
integrity constraints state that any attribute of a primary key cannot take a null value. This is because the primary key is used to identify individual tuples in a relation. You will not be able to identify the records uniquely if they contain null values for the primary key attributes.
Okay. So there are two types entity. Okay, first we'll take a recap from what we learned in this constraint. So constraint is basically limitation that we add on the values, what we're going to allow to be inserted, deleted, or modified. Different types of constraints. One is domain, then we have key, and then we have integrity. Domain means that a particular value cannot be multi-valued. It needs to be atomic. Key constraint says that no two tuples can have the same key. And then we have the integrity constraints, which is of two types: entity and referential. Entity says that any attribute of a primary key cannot take a null values. You can't put null in a primary key because they're used to identify a record. So we can't identify a record if we don't have an ID. So primary key shouldn't be null. And the referential says that I think it's more to do with when we have the relational database like multiple tables. So let's see. Go on.
Referential integrity constraint is specified between two relations and used to maintain the consistency among them. It is enforced through a foreign key. In this, the database must not contain any unmatched foreign key values. For example, any value existing in the C attribute in R relation must exist in the C uh, hashtag in S relation, and they should be of same domain. In the example below, every value of C in instance R is matching with the values of C in instance S in some tuple. R contains C1, C2, C3, C5, and S contains all these values. Thus, the instances R and S do not violate foreign key constraint.
Okay, so specified between two relations. Hmm. This constraint is specified between two relations used to maintain consistency among them. It is enforced through foreign key. In this database must not contain any unmatched foreign key values. For example, any value existing in C attribute in R relation must exist in C. Every value of C in instance R is matching with the value of C in instance S in some tuple. The R contains the values da 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 and S contains the values this. Okay. Yeah, so main thing is that the database should not contain any unmatched values. Okay. 1 second. Okay, go on.
Characteristics of an ER model. Entity relationship model is a high-level conceptual data model. It allows you to describe the data involved in a real-world enterprise in terms of entities and their relationships. It is widely used to create an initial design of a database. It provides a set of useful concepts that make it convenient for a developer to move from a basic set of information to a detailed and precise description of information that can be easily implemented in a database system.
Cool. Let's stop here. This last one was just to record your voice and send it to you. So listen to this and see how
Okay.
you're sounding. Mike. We'll stop here and we'll meet tomorrow. And probably, I think I'll be in Himachal Pradesh tomorrow. So I'll speak to you from the mountains.
Oh, nice.
Okay then. So, bye.
Bye.
Bye.